Welcome everyone. Today we have Kopp from Louisiana State talking about Shintani Faddeev Modular Cocycle.
Thank you very much for that introduction and for the invitation. So I'll be talking about something I'm calling the Shintani Faddeev Modular Cocycle, which is in some forthcoming work. But I'm going to start by talking a little bit about Hilbert's 12th problem and the Stark conjectures. So just some big picture background here. You've probably seen the Kronecker-Weber theorem. The abelian Galois extensions of Q are generated by roots of unity. There are subfields of cyclotomic fields. For example, quadratic fields can be written using Gauss sums, that they're contained in cyclotomic fields, right? And so this is a classical theorem, and there are also so Hilbert's 12th problem asks for an extension, where Q is replaced by a general number field K. What are the abelian extensions of K, and can you realize them as special values of analytic functions? You realize them as being generated by special values of analytic functions, right? And in the case of imaginary quadratic fields, this is Kroneker's Jugendrum and the theory of complex multiplication for elliptic curves completely answers this question. But for other fields, there's no general solution to this, at least in the complex analytic setting. But one step toward a solution is the conjectures of Harold Stark from the 70s, which I'm going to give you a few examples of. So in the case of the relevance to Hilbert's 12th problem, they're asking about some sort of special value of some sort of L function that's supposed to be the logarithm of an algebraic number, actually an algebraic unit in some abelian extension of the base field, where V of S is some linear combination of Hecke L functions for K. More generally, the Stark conjectures are about a generalization of the class number formula, right, which involves a regulator, and so it's what's the analog of the regulator for Artinel functions. But I'm not going to take that perspective in this talk. I'm just talking about rank 1 regulators. So here's a simple example. So here's a formula that you can prove using calculus. And the left-hand side, you can interpret that as the value of L of 1 chi, where chi is that Dirichlet character 2 on n, which is associated to q joined root 2, and the right-hand side involves a unit 1 plus square root of 2 is fundamentally a unit of q joined root 2. So just I said, so how would you prove this? Anyone know off the top of their head? No, you can
maybe express this as like the sum of two logs this series.
Yeah, so you want to put out of 2 what series?
Log.
Yeah, so that's right. So you want to put in, so instead of thinking about it, I said this is a special value of an L function, but I want to think about it as a special value of something else. So instead of putting in powers of S, make it a power series, put in t cubed, g to the 5th, etc. And then you can write that as log of some function of t. Plug in t equals 1. So that is, and so, yeah, so the before I move on, this is sure this is a trivial example, but the motivating idea is, you're not gonna, or I don't think you're going to prove cases of the star conjecture just by thinking about L functions. You want to think about, you want to introduce some other parameter that end up landing somewhere where you think about special values of something else. Like in the imaginary quadratic case, you want to think about special values of modular functions, which I realize I don't actually have that on the slide, but I'll just say a little about it. So the left-hand side here of this formula, this is a difference of two partial zeta functions, or twisted. You can think of them as twisted Eisenstein series, and if you replace this quadratic form here, which is the norm form for the ring of integers of q giant square root of 3 with like an arbitrary quadratic form in terms of a parameter tau, you can get log of some sort of modular function over there where that epsilon to the 1/5 is. It's like a theta function divided by an eta function. And that's that formula. For the twisted Eisenstein series is called the Kronecker second limit formula, and then you use CN theory to get that theta value is algebraic, and it's in this particular ray class field. So geometrically, this is related to 5 torsion points of y squared equals x cubed plus 1. And here's another example where the conjecture is open. So the interpretation of the left-hand side is going to be some limit about L function attached to q giant square root of 3. You've modded out by the action of the unit group, which gives you this cone that you're summing over. There's an epsilon there that I've written the minimal polynomial for, so you can see that it's a unit. But this equals, maybe you should say equals with a question mark. This is, you can calculate both sides to 1,000 digits. Not using this sum, but using some equivalent series that converges faster. Not so hard to do, but then actually proving that equality is, who knows? You don't know how to do it. And so this will be a bit of a running example. Okay, so just really just a little bit more background of say a little bit about class field theory. So if you've got a number field and an order in K and an ideal of the order and a subset of the set of real embeddings, you can associate a Ray class group. And so for the classical, so this is just, I should say, the regular class, the usual class group is fractional ideals modulo principal ideals. Now I want to mod out by, I want to make the denominator smaller. I want to restrict to ideals that are 1 mod m. And if you do that, you have to put in this co-prime to m in the numerator to make it make sense. This is the explicit classical definition. You can do this with the dells in a different way if you want. I've also put the word invertible there because I'm doing non-maximal orders. This is not, thinking about non-maximal orders is for array class groups is not an original idea to this 2023 paper of Ligarius, but I'm using the definition that, you know, I wrote down in that paper, and it sure is right. So, but yeah, it's so class field theory will associate to the array class group array class field, and the array class fields give you all abelian extensions as subfields in the same way that cyclotomic fields, you know, quadratic fields are not cyclotomic fields, but every quadratic field is contained in a cyclotomic field. Proper vapor situation. Okay. I should say, feel free to interrupt if you have a question. So I need some zeta functions. That's the usual partial zeta function. You know, and you know, O is a general order, but if you just want to think about the maximal order, that's fine. R is going to be some particular class that just it's like a -1 element, and then you can take this difference, which this series converges for real part of s greater than 1. There's a pole at s equals 1 that's killed off by taking this difference. So, and you know, there's an analytic continuation, and this one is going to be okay. And so the special case of you know, Stark's conjectures I'm dealing with in this this talk, it's the real quadratic base field, and you have a array class modulus that's M, and one of the two infinite places. I like to do infinity 2, so that infinity 1 is unramified. If infinity 1 is like the square root of d goes to square root of d embedding. You pick an array ideal class and associate the array class field and extend one of the row 1 embedding. Then you have two, you'd say, you know, so one is, you know, this is the key point is that the special value of the L function, which is some, you know, complex number, or, you know, some real number, turns out to be the logarithm of a unit in this array class field. And then there's also a compatibility with the argument, similar to, you know, Schindler reciprocity. You know, often this is just stated as, you know, epsilon is the Stark unit and the other Stark units are the Galois.
So how you mentioned some example that was checked numerically. How many of these have been, is there a lot of numeric experiment to check this number?
Yes, there was a lot of numerical. I'm going to mention later in the talk some numerical things that have been verified for like top cases where the degree is 10,000.
I think in some computer programs this will always work because it uses Stark's conjecture.
Yeah, it's not using that. So yeah, this is yeah. So in Paris uses Stark internally.
Okay, that's not what I want to hear.
That's how. Yeah, you've got to check that a bunch of things are unramified. Yeah, maybe I was lying a little bit. I don't think that all the local conditions have been checked in this example I'm talking about, but there was a lot of numerical. So just as an aside, since there's been a lot of work, a lot of, you know, papers on the archive about with things about Stark in them in recent years. So I just want to say a brief aside. So there's very little progress on the original Stark conjectures since Stark's work and Shintani's work that I'm going to say a bit more about in this talk. But there's been a lot of progress for p-adic L functions. So just high level overview, Dasgupta and Kakde and have proven, they proved a lot of cases of the Brömer-Stark and Gross-Stark conjectures to give a p-adic solution to the Hilbert-Solf problem for real quadratic fields, with the caveat that for a given base field, it's using infinitely many QPs. And this has been very recently, that there were some, there was a tensoring with Z join a half that was happening, and that's been removed in this to give the full Brömer-Stark conjecture in this recent work with Jesse Silverman and Ju Wang. And all of these, there was cocycle in the title of this talk. These papers use a different type of cocycle called Eisenstein cocycles that are related to Eisenstein series and were originated with Robert Scheck's work. I'm not going to say anything more about that, but I wanted to mention it. Okay. Now, separately, in the real quadratic case, there's some work of first Darmon and Vonk, and then Darmon, Pozzi, and Vonk on p-adic Stark units, connecting them to what they call real multiplication values of rigid meromorphic modular one cocycles, which are kind of a natural analog to zero cocycles are just invariant functions, or zero meromorphic function valued cocycles are, the same thing as invariant functions, which for a modular group would be modular functions. And so this is some sort of, homological analog of, CM values of modular functions but there's no geometric interpretation akin to elliptic curves, which is why a lot of this is conjectural. And the work I'm talking about in this talk could be thought of as a complex analytic avatar to this rigid meromorphic situation. So I'm going to be talking about real multiplication values of some sort of complex meromorphic cocycles with a modular function. Okay. Okay, so just a very sketchy version of the main theorem. There'll be a less sketchy version of later. The Stark class invariant, meaning the special value of the L function that's supposed to be a unit for real quadratic fields, are squares of real multiplication values of some sort of meromorphic valued one cocycle that describes the transformation of the q-Pochhammer symbol under the Jacobi. Okay, so that's the very sketchy version, and I'm going to now sort of go back to basics and talk about the q-Pochhammer symbol and the modular group and modular forms stuff. Yeah, so I'm actually I'm gonna hide the Jacobi group and just talk about the modular group. This parameter R. So R is going to be just a rational vector. Tau is in the upper half plane. Tau is going to later be in a larger domain.
That your picture on the left?
That's my picture on the left. Yeah. So making sure it's still there. So this pi r of tau, that's the var pi, not an omega bar. So pi r of tau is I'm going to define to be this is the q-Pochhammer symbol, where Q is E of tau. It's explicitly this infinite product, which converges for tau in the upper half plane. And we can ask, how does this transform under the action of SL2C? And so it's some reasons why this is a natural question. Well, okay, if you take R to be a half integer, you can always shift R just to by an integer vector, and that's just like changing that product by some finite product. So for the half integer cases, you get these theta quotients, or sorry, eta quotients, which up to fractional powers of Q, or Q being E of tau, are weakly modular for let's say gamma 2 with a character. And that's actually an if and only if. I'm not going to prove it's an if and only if, but it's if you take or if R is not a half integral vector, they won't be modular in the classical sense. Okay, so that's not the end even to the sort of classical story, because you can ask what happens when R is not in half of Z squared, and the standard answer to that is, well, you wrote down half of the product that should give you a theta function. So this is going to be the theta function. This is maybe slightly different notation than you might see elsewhere. This is, but to make some formulas nicer, but you can see that that's some Jacobi theta function, and it's a weight 1/2 modular form with character for the group gamma R, with gamma sub R is going to be A in SL2Z that fix R by 1 mod Z squared. And these are all congruent subgroups conjugate to gamma 1 of n, where n is the LCM of the denominators of the R1 and R2. Okay. And here's a theorem. The product, if you put in pi minus R and take the product, you get some easy stuff times this modular function. And this is, so that's the denominator there, that's the minus. Oh, I already wrote it. Yeah, the dedicated function. I tried to have all the definitions on the slides, and it was there. But yeah, well, that's the theta function divided by an eta function. There's a both weight 1/2, so the whole thing is weight 0. And this is just the Jacobi triple product identity with that after a change of variables. Okay, so it's not, so I'm since I'm saying this is not the end of the story. I'm going to ask the same question again. What happens for R not in 1/2 Z squared? And an alternative answer is we can weaken the notion of modularity. Okay. So for each matrix in gamma R, I'm going to associate a meromorphic function. I'm using Hebrew letter shin here, shin RA of tau, on this the domain that I drew on the board. If C is negative, the red line goes the red ray goes the other way. So I've put my name on this theorem, but it's sort of there's a lot of closely related things in the literature, both on the side of number theory, going back to Shintani, as well as some of the mathematical physics literature and conformal field theory literature, going back to Faddeev. So this is the for A being the S matrix, this function is called the Faddeev quantum dilogarithm, or a non-compact quantum dilogarithm, and it's also related to Shintani's double sine function, which I'm going to talk about in a few slides. And specifically the Sarkisian and Spiridonov paper essentially write down this function, but I couldn't find a statement in their paper that directly implies this. Yeah, but I'll give a brief sketch of that proof. So if so SL2Z is generated by the S matrix and the T matrix, T being 1, 1, 0, 1, and that's just a shift.
Sorry, is there a corresponding statement if A doesn't fix R, but you just shift the evaluation point? Like,
yeah, there is.
Okay.
So A is there we go. Yeah, so here we go. So yeah, so for T it's easy, but for S it's a theorem of Shintani. This is from one of his papers on Kronecker limit formulas for real quadratic fields. There's this function here, the double sine function, which is, for now, I'm just telling you that it's some meromorphic function of z and tau, where tau is not a non-positive real number. So just absorbing this other sort of junk into a function S sub S of R. Okay. And then
is there a way of getting these from Eisenstein?
There's a way of getting them from no, but there's a way of getting them from partial zeta functions on a cone, which I'm going to say in a minute. Yeah. So yeah, I don't know of any connectionized that series. If there was, that would be maybe very useful. But yeah, a modular transfer. So so just briefly, you can decompose A and SL2Z in terms of S and T matrices, and you can just use the two transformation laws. You have to, there's some care in the choice of decomposition to get the domain.
what is the nature of is it a really terrible singularity along that line?
Yeah, it's a really terrible singularity. There's a connect, if you approach like rational points along that line, there's a connection to quantum modular forms and you get something interesting potentially. But it's.
So normally when you give a transformation property in terms of the combinatorial group theory of gamma,
yeah,
like you are here, then it's usually transcendental and non-congruence groups come in. Is that, so this S of A, so like even the Dedekind data function.
Yeah.
I mean, you know what I'm talking about, because you get Dedekind sums is how the Dedekind data function.
Yeah, so you get.
So is there an issue, is there some feature like that?
The Dedekind sums show up. Yeah, so it's yeah.
Right, so
there's a yeah. So in this.
okay.
Yeah. So that. Yeah, the Dedekind sums.
So that's sort of a transcendental step when you take a 2x2 integer matrix, write it down combinatorially.
Yeah, so you
say the answer depends on this combinatorial representation in the group.
Yeah, you can do it in a canonical way using a continued fraction decomposition, okay. And that is specifically how I connect it to Shintani via other things. So the double, so yeah, so just how is this function actually defined? well, it's defined in terms of a double zeta function, which is, that's the definition for real part of s greater than 2. You want to meromorphically continue it, evaluate it, or evaluate the derivative at s equals 0, and that defines something that's going to be called the double gamma function. Why is it called the double gamma function? Well, if in the one-dimensional case where it's just a single sum, so you just have one omega and z, this is a Hurwitz zeta function, and you've got a gamma function.
What is rho 2?
Rho 2 is a factor that I'm not defining, that I'm dividing out in the next step. Thank you for asking. No, it's a specific thing in Shintani's paper that has some complicated expression.
Double gamma, if I shift z by omega 1, will it change by an ordinary gamma function?
It changes by, yes, it does. Exactly right. So if you omega 1 equals omega 2 equals 1 is the Barnes G function. This is like a double factorial. Factorial of a factorial. Yep. So that's exactly right. And so then this for the n-dimensional version of this, to get the analog of the sine function, in one dimensions, that's a in one dimension, that's a product of two gamma functions with the function formula, and in odd dimensions, it's a product. In even dimensions, it's a quotient. Right. Let's just say this is what I'm calling the double sine function, and there's a homogeneity relation that allows us to get rid of one of the omegas. So that's now agrees with the notation before, sine of z tau. And tau here can be real or complex, but it just can't be negative or 0. Okay. So now I'm going to say if you're looking for like lots of cohomological stuff, this is going to be disappointing, but this is just to define, in as direct a way as possible where this cocycle is going to live. Say again, for a discrete subgroup of SL2R, which is just going to end up being that group gamma R. Say a system of domains is a collection of open sets, possibly larger than the upper half plane, contained in the Riemann sphere, indexed by A and gamma, and a weight cocycle. It's going to be a collection of meromorphic functions WA defined in D sub A that satisfy cocycle condition. So it's a multiplicative cocycle condition. And the co-boundaries are going to be co-boundaries of things that are come from meromorphic functions defined on the union of all of these D sub A's, which here will be like the complex plane. Okay, and then I'll denote the quotient group like that, which suggests that maybe there's some more going on, but just that I've got the data of gamma, D sub A, and sheaf of meromorphic functions, which you could replace by analytic functions if you want to be more restrictive. But the feature that distinguishes this from just like standard group cohomology is the domain of these functions depends on A. So there's some equivariant to it. So you can think of this as the first cohomology of some equivariant check complex after taking gamma invariance. There are a couple not quite equivalent ways to do it, but I'm not going to get into. But for a really simple example, you could just take C tau plus D. That's the cocycle that a modular form transforms by. And that is a cocycle in this sense. And since I said meromorphic, I could really just take the A to be C. That for analytic. And then this map from then the map fix R and consider the map from A to Shin RA. That's going to be what I'm calling the Shintani Faddeev cycle. And so now I want to tell you how to take the real multiplication values of a cocycle. Now
Groups
restrict them.
sometimes be non-congruent.
What's that?
Your groups, gamma is a finite index subgroup.
Yeah, I like to just write down the most general definition that makes sense.
No,
Yeah,
but
it makes sense for non-congruence, but these are congruents.
They are congruent.
My groups are all congruents. W wave tau is some weight cocycle in this sense for some DAs. And I'm going to fix a real quadratic number beta. And I'm going to fix a positive generator for the stabilizer of beta in gamma, by which I mean one such that this is supposed to be an eigenvalue. An eigenvector that I want the eigenvalue to be. You could do this in the parabolic case as well, but then you would need a different positivity condition. So, so in the, and so then if you want to evaluate, the cocycle and add a real number and get a number, you have to first evaluate the A, which is defined in terms of beta to get a function, and then evaluate the function at beta, and that gives you a number. And this is only going to depend on beta and on the cohomology class of W in this cohomology group. Which means the hope is that these RM values contain some arithmetic information. If I've not quite defined, my special function right, since this is a cohomological invariant, that suggests that it'll get rid of any extra junk that's in the definition. White out. And so if you've, I guess if you've seen the rigid meromorphic cocycles stuff that Dharma and Potsy won't work, their situation is different because they're evaluating at a point in the p-adic upper half plane, so they don't need to do this sort of equivariant thing with these different domains. It's all just the p-adic upper half plane. So it has formally it looks the same, but it's a very different flavor. So just here's another exercise. If you've done the power series already, you can write down the standard C tau plus D cocycle, fix beta a real quadratic irrational, and B, factor B, the associated lattice in the real quadratic field, and then you look at the multiplier ring, the associated order, and then the exercise is the RM value of this cocycle the easy part is it's a unit and it's totally positive. The trickier part is it's the generator for the totally positive part. So in the maximum order generator. Okay, cross plus. Okay, so all right, and so here's a still somewhat sketchy but less sketchy version of my main theorem. So same setup. Beta is real quadratic irrational. B is the associated lattice that's going to be an ideal of order O. R is a rational vector. Then this Rm value is some 24 nth root of unity that can be made completely explicit times a square root of the star class invariant. The thing. So the square root, this green square root should be a star or a square root of a star unit, and so this ray class and the modulus for the ray class are both obtained from the data of R and beta. And so I think this next section I should probably say, the case of the maximum order, but with the Galois partial zeta functions versus the order partial zeta functions, there's some discrepancy there that needs to be dealt with. This is supposed to be an algebraic unit that generates the ray class field MO infinity 2 for the order. And moreover, the square root should also be in an abelian extension of the real quadratic field. It's part of Tate's refinement. Tate's refinement is probably most known for saying, this is all like at the Archimedean place. There's a version of this story at the non-Archimedean places, but that paper of Tate also contains this conjecture about the square root being an extension.
But this distinguishes one of the square roots, like it's not always the positive one.
Yeah, so here the square root is just the positive square root. And maybe I should say that there's a plus or minus one ambiguity in there. I think in previous talks I've put the square over here, and the square of this is some kind of metaplectic character. It's a product of a theta character and an a character. There's you can write down some sort of combinatorial expression for that sign in terms of continued fractions and stuff, but it's not that pretty. So it might turn out that I might end up stating the theorem for the square. But yeah, okay. So so I was a little bit about the proof. The Jacobi triple product formula gets used, which I already talked about. And then I'm specifically using Brett Tangedal's refinement of Shintani's formula, which uses a continued fraction expansion that builds on some work by other people. So that's telling you how to get the square root as a product of double sine functions, and then if you can telescope that product down using the cocycle ignition, but you need to know, you need to set it up right in order to do that, and you also need to keep track of the units or the roots of unity, which are quite complicated. And so there's a lot of work in the paper goes into like messing around with continued fractions and needs and data character to get that down to a nice form at the end of the day. Right, and I mentioned Brad Tang et al., but that's a lot of the there's a lot of previous work on the Shintani formula from Arakawa, Hayes, Shack, Tang et al., that is relevant to the story. Okay, so some examples. Here is the case where you just have the vector R is an integer vector, so this will just fall out from the transformation formula for the Dedekind eta function. I guess by the formulas from the beginning, you could do the same thing for half integral vectors. So this mu is the Meyer invariant, which is a shift by 3 of the Rademacher invariant. Which is expressed in terms of Dedekind sums, and then this, and so the corollary would be, the special value is, 24th root of unity times the square root of this fundamental unit, fundamental totally positive unit. Okay, and then here is the big sum that I said was an open conjecture. This is the set. This is that rephrased as an RM value of the Shin function. So the R in this case is 0, 1/5, and the beta is 2 plus square root of 3, and that's supposed to be, well, that's explicitly with this matrix A that stabilizes everything. So it's that 20th root of unity there, or 40th root of unity there, times square root of nu, where nu is the root of that polynomial, which is a unit in the correct field. But again, the theorem is that this is equal to the L value. The part that we still don't know is that it's actually algebraic. Okay, so so I want to say a little bit about some joint work I'm doing with some people in the field of quantum information theory that is built, it also relates to a previous paper of mine. And this, so complete change of topic that I promise will connect back. And yeah, this will only be about 5 minutes. So a seek or seek pavam, which is some long acronym, is a set of quantum measurements that is equivalent to d squared equiangular lines in C to the D with the Hermitian inner product. So for example, for d equals 2, lines in C squared are the same as points on P1 of C, which is the same as points on a sphere. All of those equivalences are like preserve the metric. And so for equiangular lines is the same as the 4 equally spaced out points in the sphere, which are the vertices of a regular tetrahedron, written explicitly on the screen. Okay, so in D dimension, so in 5 dimensions, you want 25 equiangular lines on C5. Well, the conjecture, which was surprising when it was formulated because of the similar sorts of questions about real equiangular lines. You usually don't have these maximal sets of equiangular lines, so this is from Gerhard Zauner's thesis. He conjectured that there was always a seq in dimension D, and moreover that the construction comes out of this Weil-Heisen d-dimensional representation of the Weil-Heisen. So that dimension is that representation is the Weil representation or the Schrödinger representation, or it gives the Weil representation of SL2 of Z mod DZ related, so related to lots of nice things in physics and mathematics, but there's a lot of numerical data. Seqs are known in up to dimension 53 and in other dimensions as large as 1299, and there are some algebraic, this is like explicit algebraic solutions with sometimes with these huge degree polynomials showing up, and there are numerical solutions in some even more cases, nonetheless, we only know this conjecture in finitely many cases. Okay, so the observation of Appleby, Flamia, McConnell, and Yard. So Appleby, Flamia, and Yard are all physicists or quantum information theorists, whereas Gary McConnell is actually a student of John Coates. So they observe that these seqs, or the vectors appearing in these equiangular lines, appear to be in some abelian extensions of a certain real quadratic field. This might look like a thin family of real quadratic fields. It is not. You get every real quadratic field in this way by Pascal. However, and more specifically, there were some explicit predictions about what class field these seqs should live in. And I observed that some certain data that characterize these seqs appear to be related to Stark units, and I made this more precise when E is 2 mod 3 and a prime, which is the prime case in the quadratic field. Okay, and so more recently, I've been working with Marcus Appleby and Steve Flamia on a generalization of this that will tell you, give you a general formula, still a conjecture for all of the known examples of these seqs, as well as some previously unknown higher rank analogs of seqs. So Zauner's conjecture so seq existence would follow from Tate's refinement of the Stark conjectures plus a certain special value identity for this this cocycle, and in the other direction, if you knew that this construction worked, you could say something about the Stark conjecture. It wouldn't immediately prove Stark there, but it would reduce verifying cases like the one I said before was open to a finite Kroner basis calculation. Yeah, and so that's where I'll stop for now.
Any questions, the speaker?
The special value conjecture.
Yeah.
What is it?
What is it? It's so it's I'm not going to write it exactly, but it's a quadratic. So it's the projections onto the equiangular lines are so you can write down a formula for what those projections should be, and verifying equiangularity is easy. Verifying that they're projections is not. So if you write down the condition, pi squared equals pi, that gives a bunch of quadratic conditions on the values of the Shin function. And so though it's a quadratic condition that looks kind of like a twisted convolution of these Shin values is equal to one of these Shin values. And it doesn't seem to be true. I haven't been able to get any continuous version of it that seems to be true. It seems it's special to these special values. So that's why I said special value identity, special function identity. Special function identity would be much better place to be. Yeah. So that's is that specific enough for you, or do you want me to say more?
It seems to me that you'd answered their question subject to what you might call some by now standard conjectures. I was just trying to understand.
Yeah. So I have not answered the question subject to standard conjectures. I've come up with a new conjecture but it's more like I've distilled down the problem that needs to be solved.
And in the cases, in the examples, it works out.
Sorry, in the
examples that have been constructed.
Yeah.
It works out.
It works out in all the examples that have been constructed. Yeah. And we found some new examples.
That was going to be a question. Did you find any new examples?
Yes. So in my at the time of my release of this paper, dimension 23 had not been done, so I did the first 4 primes that were 2 mod 3, and 23 was new. We've for the newer work, dimension 100, there was one up to symmetries. There was one example of a seq that was known. Our framework predicts there should be 4, and we found all 4. It were directly constructed all 4. We've verified a bunch of smaller examples. And, I think currently we're in the stage of just trying to get a paper out, but then Steve Fleming is writing some code that should check some more cases.
I just want to emphasize what you said. The quadratic relations you mentioned, Stark unit, are really completely new. They're not related to anything either in Stark nor in Take.
Yeah, that's right.
Questions? Okay, let's thank speaker